So now we have right endpoint formula, a left endpoint formula, and we're going to generalize this a little bit to create a thing called a Riemann sum. This is after the mathematician Riemann. And a Riemann sum is the left and the input and right input approximations are examples of Riemann sums. But specifically, what is a Riemann sum? Okay, so here's our definition. Let me erase some of this. So let's say we have a function defined in a closed interval. A, B, and then we have a partition of the interval. i.e. we've split AB up into a bunch of little subintervals. Okay, and each subinterval, using the same notation we had before, let's let delta x be the width of each subinterval. Okay. And each subinterval can be expressed abstractly as follows. X sub I minus 1 to x sub I. So this would start at x0 to x1, x1 to x2, and that would be our partition. Okay. And so for each I, value of I, and here's the kind of new thing, let x sub I with a little star up here be any point in that subinterval. Okay, so we're no longer holding ourselves to the left endpoint or the right endpoint. It's just any value in that subinterval, we can choose it. Okay. Then the Riemann sum for f of x is as follows. Sigma notation. Index I goes from 1 to n, and the function is evaluated at any point in each subinterval times delta x. Okay. So that is a Riemann sum. So basically it's just kind of a generalization of the left or the right endpoint formulas that we were already working with, and basically just saying that we're going to form this sum by choosing any value within each little subinterval to plug into the function. Of course, there's a lot of questions that leads to, like, does it matter which one you plug in, and where is this going anyway? So the big idea is, as we've mentioned before, is as we increase the number of rectangles in our partition, so we kind of make our partition more and more fine, then the approximation gets better, okay, to the area under the curve. Remember, this whole thing is about finding the area under a curve. And so here's the big result. So assuming f of x is continuous, non-negative over AB, and we have a Riemann sum for the function, then the area under the curve of y equal f of x on AB is, so area A, so A equals the limit as n goes to infinity of this Riemann sum. Okay, so this is big. Let me draw a little picture to kind of illustrate what in the world we're talking about. Oh, and I guess let's also make it clear. F is continuous and non-negative for the moment, okay? Own the interval AB, because that's all we really care about at the moment. So here we've got AB, we have some function f of x, and we have partitioned a to b as we have discussed. Okay, so this is x sub 0, x1, x2, and so forth, and that's up to xn. And then these Riemann sums, we're just choosing, as I said before, for the ith interval. So let's say that like this is the ith interval right here. So that's xi minus 1 to xi. We just choose some value in here, okay? It doesn't have to be the left one, it doesn't have to be the right one. It's just x sub I star, okay? And the interesting thing is that it doesn't matter what point you choose, whether you choose a left endpoint approximation, or you choose a right endpoint approximation, or you choose a middle value. If you take the limit of this expression and let the partition get finer and finer and finer, they will all approach the same value, assuming the function is continuous, non-negative, etc. And that's not immediately clear, so there's a proof for this. We're not going to go into the proof, but I just want to point out that this is not something that is just accepted without proof. You know, this is we're making some claims that this limit actually exists and is unique and doesn't matter on what x value you choose. Okay, but this is great because this gives us a exact area formula for the area under a curve. Now, we still have to be able to actually compute it, but we do have a formula now.